How are you guys doing? This is Mike Johnson here, and in this video we're going to cover how to prove the product rule of derivatives. Product rule. Oh my goodness. The product rule of derivatives. So before we go ahead and do that, let me just go over the basic definition of the derivative of a function in regards to limits. So let us talk about the limit definition of a function. We'll say the limit definition of derivatives, of a derivative. So this, we can assume any differentiable function. We'll assume f of x is differentiable, and we can then determine its derivative, f prime of x, by taking the limit as h approaches 0 and applying f of x plus h, subtracting your original function, all over h. And I'm sure some of you learned before, maybe in a pre-calculus course or a college algebra course or an advanced algebra course, that you learned that this is also called the quotient rule. So in other classes we learned how to apply a quotient rule. This actually then is later used on in calculus, where we're actually able to find the derivative of a function that is differentiable. So now, since we know the definition of a derivative using the limit rule, and you should have covered this in a prior lecture, let's go ahead and assume h of x is equal to it's composed of two functions, f of x times g sub x. So we have two functions being multiplied together, f of x times g sub x. And we're going to have to make another assumption here, and that assumption is that f of x and g sub x are both differentiable. So f of x and g sub x are both differentiable. So in order for us to apply the derivative, we have to safely assume that f of x and g sub x are both differentiable. So I'm just going to put the rule over here, and I'm going to apply that here using h of x being our function. So we're going to have h of x plus h minus our original function all over h. So we have h of x plus h minus our original function all over h. So we said let h of x equal to a composition of f of x times g sub x. So we have two different independent functions being multiplied together. Our derivative h prime of x will be equal to the limit as h approaches 0 of f of x plus h. Everywhere I see an x, I'm going to have to plug in an x plus h. So this is the first part. H of x plus h, we have our original x plus h values plugged in. Now we have to subtract our original function. Our original function is f of x plus h. So we subtract our original function, f of x times g of x. And this is still now all over our value of h. We still have to divide by a value of h. So this, ladies and gentlemen, is the calculus. This is the calculus. I always say, when I teach this class, I always say that there's more college algebra in calculus than there actually is calculus. That you're actually going to do more algebraic manipulations in this course than you're actually going to do calculus in this course, which is sort of scary to say, but that's the reason why I think so many people have some troubles here, is because there are such advanced algebraic manipulations. So now there's a little trick that we're going to apply here. There's a little trick that I use in order to make this very easy. And the trick is that we're going to subtract out f of x, g of x plus h, and then we're going to add in f of x, g of x plus h. So we're going to subtract out f of x, g of x plus h, and then we're going to add in f of x, g of x plus h. So we're going to do this little trick here and see how this goes. So we are going to add this in right there. So right after this function, we are going to subtract out f of x, g of x plus h, and then we're going to add in f of x times g of x plus h. And notice, if you subtract and add the same thing, you just have a value of 0, so that means we're not altering anything at all. So this will still be equal to the limit as h approaches 0 of f of x plus h g of x plus h. Haven't changed anything so far. That's this portion. Now we're going to subtract f of x, g of x plus h. And now we're going to add f of x, g of x plus h. So that portion is now this right here. So we've just put this in, we just place this into the top. Notice this is still equal to a value of 0, so we haven't done anything to this at all, and we still have to subtract f of x, g of x from the original portion. And notice we still have to divide this whole thing by a value of h. So this whole thing gets divided through by a value of h. I say, whew, that was a lot. Okay, so if we look at this, let us keep going with our algebra. All we're doing is manipulating our algebra. I am going to go ahead and input a special set of parentheses here, and then another one here and here. So let's analyze everything in the green parentheses. Notice I'm adding between these set of parentheses, so I'm just going to split this limit up. Remember, the limit of two functions being added together is just the sum of those individual limits. So now what we're going to do is that I'm going to keep this first limit here. Limit as h approaches 0. F of x plus h, g of x plus h. So I have the f of x plus h, g of x plus h, minus f of x, g of x plus h. And this is still all over h. So I'm splitting it up right down there. So I still have to keep my limit. I can't chop off the limit because, as we said before, it just doesn't drop off. So now this will still be plus the limit as h approaches 0. We will have f of x, g of x plus h, minus this portion, f of x, g of x, and this will still be all over my value of h. All I've done is just split up two fractions. Notice if I wanted to add these back, since I have a common denominator, my numerators would just add back together. So now I want us to note that we have a common factor in this first limit, g of x plus h. So hopefully we know we can take that out. And then here we have a common factor of f of x. And notice we'll be able to pull that out as well. Doing so, we will have the limit as h approaches 0 of g of x plus h times f of x plus h minus f of x. I just factored out that g of x plus h, and this is still all over h. So notice the operation here is multiplication. Multiplication. So I can actually split this up and keep my denominator either on this side or on this side. And I hope we're starting to see now that this portion is becoming the definition of f prime of x. Noticing over here we can pull out our functional value of x. So I'm going to pull out f of x. Oh, I still have to have my limit. Sorry, I forgot my limit. As h approaches 0, I will have f of x, and this will now be times g of x plus h minus g of x, and this all will be all over h. So hopefully we can see here that this is something special and this is something special. I can go ahead and split this up and say this will be the limit. I'll move the screen up so we can all see it. The limit as h approaches 0 of g of x plus h. This will be times the limit as h approaches 0 of f of x plus h minus f of x all over h. Notice I'm multiplying these two together. This is really g of x plus h all over 1. Multiply our numerator straight together, multiply our denominator straight together, and we have the same exact thing. And notice here I'm going to split the second portion up the same exact way. So I'm going to have plus the limit as h approaches 0 of f of x. This will still be times the limit as h approaches 0 of g of x plus h minus g of x all over h. So notice this is still all over 1. So now, hopefully this is becoming more transparent about these two limits over here. So notice these two limits are just the definition of the derivative of your original function f, and this is the definition of your original, this is the definition of the derivative of your original function g. This is the definition of the original derivative, this is the definition of the original function's derivative f of x, and this is the definition of the original function's derivative g prime of x. So now we will have the limit as h approaches 0. Notice if h goes to 0, this goes to 0, so we're just going to be left with g of x. This is f prime of x plus this goes to 0, does not affect our function f of x because that's just constant. So we'll just have a functional value f of x, and this all is g prime of x. So notice here we have the derivative with respect to x of f of x times g sub x equal to g of x times f prime of x plus f of x times g prime of x. There are a couple ways to go about proving the definition of the product rule, but this is one that I actually think is a little fun. It gives me some good practice on my algebraic manipulations, and usually most people don't have a problem understanding it. But if you do, go back and watch it a couple times. Otherwise, shoot me an email. I'd be more than happy to help you out. Take care.